Welcome to the Explainer. You know, computers, they think in ones and zeros. But us, we think in poetry. We make jokes, we get into arguments. It's a totally different world, right? So how on earth do we bridge that gap? Well, today, we're going to pull back the curtain on the blueprint that actually teaches a machine how to understand our language.
So that really brings us to the big question, doesn't it? How do you teach a machine, something that is built on pure cold logic, to understand something as messy, as nuanced, and let's be honest, often totally illogical as human language?
Okay, so here's how we're going to tackle this. First, we'll look at the basic blueprint for language. Then, we'll see how a sentence actually gets built. After that, we'll dive into where these blueprints go wrong. Then we'll check out some more powerful blueprints. And finally, we'll see how all this theory actually shows up in the tech we use every day.
Right, so to teach a machine language, you can't just talk to it and hope for the best. Nope, you need to give it a super strict set of rules. Think of it like a detailed architectural blueprint for how to build language, piece by tiny piece.
Now, the official term for this kind of blueprint is a formal grammar. And honestly, the best way to think about it is like the ultimate recipe book. It's not just suggesting ingredients, it's giving you a precise, step-by-step formula for creating sentences that are, grammatically correct.
So any blueprint like this is going to have 4 key parts. First up, you've got your terminals. That's just a fancy word for the vocabulary, the actual words like cat or eats. Then you have non-terminals. These are the abstract building blocks, concepts like a noun phrase. The start symbol, which is just S, is our main goal, a complete sentence. And finally, and this is the important part, you have the rules that tell you exactly how all these pieces are allowed to fit together.
Okay, so we've got the pieces and the rule book. Now for the fun part. Let's actually put them to work and see how this blueprint builds a sentence, right from scratch.
All right, so we start with our goal, S for sentence. The rulebook says, okay, a sentence can be a noun phrase plus a verb phrase. Cool. Then we use more rules to break those down into smaller and smaller building blocks. Until, boom, we finally get to a point where we can slot in the actual words from our vocabulary.
And there you have it, the result. By just following those rules, step by step, the system has generated a sentence that is, well, it's perfectly correct. At least, it's correct according to the blueprint we gave it.
Now, the crucial thing here is that this whole process isn't random at all. It actually creates this really logical structure called a derivation tree. You can kind of think of it like a family tree for the sentence. It proves that the sentence is valid, and it shows how every single word traces all the way back to those original rules.
So far, so good, right? It seems like it works perfectly. But what happens when we start to push this simple little blueprint to its limits? This, my friends, is where things get really interesting.
Get this. Our grammar also allows for this sentence: the cheese chases the cat. Now, if you look at the rulebook we created, this is a 100% valid sentence. All the parts are in the right place. But in the real world, that makes absolutely no sense, right?
And that right there points to a huge limitation of our simple blueprint. See, it's a master of structure, of syntax, but it has zero, and I mean zero, understanding of meaning, what we call semantics. All it cares about is whether the pieces fit together correctly, not if they actually make any sense.
Oh, but it gets worse. What happens when the rules don't just create something that's nonsense, but they create actual confusion? I'm talking about sentences with more than one possible meaning. Take a look at this rule. You'll find something like this in pretty much every programming language out there. And on its own, it looks simple enough, right? But this little rule introduces a classic and really tricky problem.
So when we try to apply that rule to a more complicated, nested statement like this, a huge question pops up, one that our grammar on its own has no way of answering.
So who does that else belong to? Does it go with the first if or the second one? The thing is, depending on how you decide to build that derivation tree we talked about, you get 2 totally different results. This is what we call ambiguity. And for a computer that absolutely needs certainty, this is a massive problem.
Okay, so to get around these big problems, the lack of meaning and all this ambiguity, we clearly need better, more powerful blueprints. The simple rules just aren't cutting it anymore.
This is where computer scientists came up with more powerful blueprints. For instance, there are things called context-free grammars, and these are great at handling perfectly balanced patterns. Think about it. In programming code or in a math equation, every single opening parenthesis needs a matching closing one, right? Our first simple grammar couldn't guarantee that, but these more advanced versions, they can.
And it goes even deeper. There are even more powerful blueprints called context-sensitive grammars. These can enforce rules based on context. So, for example, imagine in a programming language where you have to check that a variable was actually defined before you try to use it. That means the grammar has to remember stuff from earlier in the code. We're talking about a whole new level of complexity here, way beyond just fitting pieces together.
I know, this all might sound super abstract and theoretical, but I promise you, these blueprints are the hidden engine that's running behind so much of the technology that you and I use every single day. Seriously, every time you compile code, or your browser loads a web page, or you ask Siri or Alexa a question, heck, even when you use a simple spell checker, you are using technology that is built on the very foundation of these formal grammars. They're in the background, constantly parsing, analyzing, and structuring information based on these exact kinds of rule sets.
And all this brings us to a final thought I want to leave you with. As these blueprints get more and more sophisticated, as machines get better and better at understanding our language, what does the future of communication between humans and computers even look like? Are we heading toward a future where those lines just blur completely?